Okay, let us start. Okay, in our previous classes, someone is again coming. I cannot allow anyone more. We can go back. Okay, in our previous classes. Okay, first tell, has my screen been shared? Can you see my screen?
Yes, sir.
Okay. Okay, which we have covered. These have been covered. So okay. Okay, law of transmissibility has been covered. And system of forces, collinear force, coplanar force, concurrent force, what are they? We have covered. Now, in this lecture, we will start what is a moment of a force. Okay. So, moment of a force about a point is a measure of its rotational effect. Just wait for a minute, I will share my whiteboard. Share the whiteboard. Okay, so moment of a force. Okay, so moment of a force. Let me draw a diagram to make you understand. Let us consider a hinge. Hinge means the joint of the door.
But I think your screen is not visible.
Yes,
Okay,
sir.
okay. Sorry, I stopped sharing. Sorry. Now it is. Okay. So what I have drawn here is a hinge joint. So that joint is a hinge joint. Okay. So it is a door. So the door can rotate about the hinge. Now say, if I am applying a force of F, okay, and this force is at a distance of, let us say, d1 from the hinge. Okay. So moment of the force will be, let us say, m1 F into d1. Okay, so it will have some particular value. If F have some value and d1 has some distance, so moment of the force, the unit of moment of force will be Newton meter, isn't it? So moment of the force is Newton meter. Now, to increase the effect of the moment, not force, we have to change the position of the force, isn't it? If we change the moment position of the force, the effect of the moment or value of the moment will be changed like that. Let me take the eraser. Okay. Now let us say I am applying the force from here. That same amount of force. Now only here in the second case, the distance between the hinge and the line of action of the force only changes. So M2 will be, force value has remained the same, into D2. Sorry, D2. Okay, so value of moment for point 2, or when the force is applied uh, at the extreme end, the value of the moment has become more, as the forces value remain the same for the both the cases. But the value of the distance of the force from the hinge as changes in the second case, so value of the moment also changes. So to give the practical example, we can say that for a door, from our practical experience, we know that when we apply the force from the extreme end of the door, the rotation of the door becomes easier, isn't it? But if we apply the force, or if we try to rotate the door at a point nearer to the hinge point, then the rotational movement of the door has become very much difficult. So we have to apply the force to rotate the door from the extreme end of the door, isn't it? So this is the basic concept of the movement of the door. But when the force is applied here, let us say force. If the force is applied here, right at the hinge, let us say F, then the moment value is 0, as F into 0, as distance from the hinge of the force has become 0, so the value of the moment has become also 0. So here, if we apply the force at the hinge, so no rotational effect will be there, isn't it? From practical experiences, we know this. Okay, so from practical experience, we can say that if we apply the force at the hinge, there will be no rotational movement, and to rotate the door easily, we have to apply the force at the extreme end. So this is the primary concept of the moment of the force. Now we'll move to a theorem, Varignon's theorem. Just wait now. Okay. Now, if you see my screen here, please see here. So the Varignon's theorem, to solve to apply the Varignon's theorem, we need the concept of the moment. So that's why I have taught you the concept of moment first. So here the Varignon's theorem states that the algebraic sum of the moments of a system of coplanar forces about a moment center in their plane is equal to the moment of their resultant force about the same moment center. Okay, so what does it mean? So we have to take uh, uh, two forces, two coplanar forces, and we need another force of the resultant force of two coplanar forces. So here we have three number of forces, actually two number of forces, and one resultant force here. Okay, so if you can see the figure here, see they have figure, I have that figure is being shared in your screen, 2.6 figure. Just refer to the figure number A. See, two forces are here, F1 and F2. I will draw it in the whiteboard later on also. Okay, so F1 and F2, two forces are there, and the resultant force of F1 and F2 is R. Okay, so the resultant force of F1 and F2 is R. Yes. So we have F1 force. Just see here at point A. Just see the figure for the time being. I will draw it in the whiteboard also. Okay. So F1 is the force, one force, and F2 is another force, and R is the resultant force of F1 and F2, and B is the moment center. Okay, the moment center has been taken somewhere outside the drawing, as here the theory says the algebraic sum of the moments of a system of coplanar forces about a moment center. Okay, moment center will have to be taken. Moment center is nothing but a center, but a point uh, about which the moment is to be taken. Okay, in their plane is equal to the moment of the resultant force about the same moment center. That means now we have to take the distances or perpendicular distances of point of all the forces from the moment center let us say the distance of F2 force from the moment center is D2, and the distance of F1 force from the moment center is D1, and the distance of R from the moment center is D. Okay, so according to the Varignon's theorem, we can write R into D will is equal to F1 D1 plus F2 D2. Okay, I'm sharing the whiteboard to make you understand more better. Yeah. Okay. Okay, now so I'm drawing now here. So we have three forces. Okay, so let us say it is the F1 force. Okay, and we have another force here, F2. Okay, now by means of parallelogram law of forces or by triangle law of forces, we can find the resultant of the forces by means of composition of the forces. Let us say the resultant of F1 and F2 is coming out as force R. Okay, I believe this concept has been understood. So we have three number of forces, two number of forces, F1, and both forces are coplanar forces. That is, two forces are will act as a same plane. So F1 and F2, and R is the resultant of two forces. And now we have to take a point outside that diagram or in anywhere. Let us say point B. So from A, the forces are acting. So point B is the moment center. Okay. So now the distance of F1, let us say from B is D1. So this is a perpendicular. I have drawn a perpendicular line from force F1 which touches the point B, and from force F2, let us say the distance is D2. Okay, and from force R, let us say the distance from the point B is small d. So now according to the, as per the Varignon's theorem, we can write the resultant force multiplied by the distance or the moment of the resultant force from the moment center will be equal to summation of the moments of the two forces, that is moment of F1 force about the point B, that is F into F1 into D1, plus moment of F2 force with respect to the point B, so the distance is D2. So this is the Varignon's theorem. Okay. So distance of R from D from B is D, small d. So R D is the moment of the resultant force about the moment center, and F1 D1 is the moment of F1 force about B, and moment of F2 force about B is F2 D2. So these are being taken. So this is the Varignon's theorem as we are discussing. So the proof of the Varignon's theorem is given also here. You may study this from the book. Okay. So here at for diagram B, if you now in that first figure we have drawn two forces F1 and F2, and B is the moment center, as I have already told you, and that Varignon's theorem has already been told. So now what we have to do here, so we have to join here. So the three forces are drawn. Okay. Now see at the next diagram, B diagram, AB is joined already, and that is taken as y-axis. So the AB means the from the moment center, the wait for a minute, from the moment center. Okay, from the moment center, B A point is joined and a perpendicular line is also drawn. I'm drawing this diagram later on also. For the time being, just understand the concept only. Okay, so now perpendicular to AB, another axis is drawn. So AB line has been taken as y-axis. Now another line is drawn from point A to make it the x-axis, and three forces are already there: F1, F2, and the resultant force R, isn't it? And the resultant force R. The three forces have already been drawn. So the angle between R and X, let us say theta. Okay, so the angle between R and X, let us say theta. Okay, so if I draw a perpendicular line from R up to point B, okay, so you can say that that angle becomes theta also. A line A, so angle A B. So I will draw the drawing in the whiteboard also. Just try to understand this. So angle ABB1 will become theta also, because x is y is perpendicular to x, and R is and that perpendicular line has been drawn from R. So with R and X, angle is theta. So perpendicular to R and perpendicular to X will make the same angle theta. So that angle will become theta. So angle ABB1 will become theta also. Now R into D is equal to R AB cos theta, because from that right angle triangle ABB1 we can write cos theta is equal to, D by AB. So D is equal to AB cos theta, isn't it? So AB into R cos theta, so AB into Rx, or X component of R is the Rx. Now similarly, for the other forces we can write F1 D1. So this is the X component of F1, and F2 D2, this is the AB into X component of the F2. So now if we add this F1 D1 plus F2 D2, we will have, now we can take AB common, so F1x plus F2x, and that is equal to AB Rx. Okay, let me share the whiteboard again. Okay. Okay, now so let us say this is the point A, okay, and point B is somewhere here. Okay, let's say here point B. So we have taken that as y-axis. Okay, now perpendicular to y, we have taken x-axis also. Okay, so three forces are already there: F1, F2, and also R. Okay, so R is the resultant between F1 and F2. So let us say this angle is theta. If we draw perpendicular to R, so this angle will also become theta, because y is perpendicular to x and a perpendicular line from R has been drawn. Okay, so this angle will become theta also. So now cos theta, from that triangle we can say cos theta is equal to d by AB. So d is equal to AB cos theta, isn't it? D is equal to AB cos theta. So R into D will be equal to R into AB cos theta. Cos theta. Cos theta. Okay. So we can write AB and R cos theta is the x component of R. So Rx. So R into D is equal to AB Rx. Now we can also write, following the similar concept, if we draw D1 and D2, then F1 D1 will be equal to AB into x component of F1, and F2 D2 can be written as is equal to AB into x component of F2, isn't it? Now if we make addition of F1 F1 D1 plus F2 D2, that will be equal to, if we take AB common, then F1x plus F2x, isn't it? Now F1x and X2x are the x component of R, so Rx. Now you see, so from these two equations, if we taken as this equation 1 and this equation 2, then see 1 and 2 are same, so we can write R into D is equal to F1 D1 into F2 D2. So this is the proof of the Varignon's theorem. Okay. So Varignon's theorem is the very much important concept. So please first you study this in your home, then we will do the numerical in the next class according to the based on the concept of the Varignon's theorem. So now I'm stopping the recording. Just wait.